Okay, so welcome to Math341. So this is lecture 17. And so what I want to do today is I want to just briefly review Markov's inequality. I want to do Chebyshev's inequality. As somebody who cannot spell, Chebyshev is one of my favorite mathematicians, not just for the caliber of the work that he has done, but for the fact that almost any way you spell his name is an acceptable transliteration of his name into English. I've been trying for years to get people to spell his name differently depending on which one of his theorems you want to use, because he's got theorems in number theory and probability all over the place. But we're going to see a huge difference in strength between Markov and Chebyshev. And I really want to spend time today emphasizing why this is not surprising and why later in the semester we're going to do even better with the central limit theorem. So we'll talk a little bit about divide and conquer in Newton's method. We'll talk a little bit about the exponential function and what do you need to make the arguments that we're going to do rigorous. Again, real analysis is not a prerequisite. Measure theory is not a prerequisite. I want to at least let you know where you have to be careful. And then we'll start talking a little bit about more special famous distributions. So if you haven't seen the Poisson, this is another great one. And a nice application of the Poisson is it gives you a simple proof of Stirling's formula to estimate n factorial. So one of the things that I love about mathematics is there's frequently more than one way to get to a result. We saw that when we did the Pythagorean theorem on Tuesday, that depending on how we set things up, we can prove the same result different ways. And they emphasize different aspects of the problem. I love the dimensional analysis because that's an idea that generalizes. So the big idea from today is the more you assume, frequently the more you can deduce. And then the other, when we start talking about Stirling's formula, is the need to estimate well. So the first time I ever taught probability was over 20 years ago. I was going to be a new postdoc at Brown. I was at Ohio State at the time, and I got a copy of the book that I was going to use. But I didn't have the current edition. I had like the second edition. I figured it doesn't really matter. Probability doesn't change that much in terms of the basics. And there was a combinatorial problem, and the answer is a simple binomial coefficient. And the book then says, and you would think you've now solved the problem. You go, no, I know I've solved the problem. And the book continues, but writing down the binomial coefficient is not enough. And I go, what do you mean? You have to estimate the binomial. How old is this book? And this edition from was like 1950s, 1960s. You didn't have the hand calculators back then. Estimating large factorials was non-trivial. And so the book actually talked about how would you estimate like that. Nowadays, we can do a lot of these calculations on computers. This is not a skill that's as important, but you want to be able to get a feel for the values of certain quantities. What size can you roughly say? Can you do some quick estimates and get an upper bound and get a lower bound and get a sense of, do you think your answer is reasonable? So I really want to try to emphasize a lot of that. Okay, so we saw Markov's inequality before. The probability that x is at least a is at most the expected value of x over a. And this is under the assumption that x is a non-negative random variable. Once you have this, of course, you can look at, instead of calculating the probability that x is at least a, to the probability that x is strictly less than a. If you're dealing with a continuous random variable, you don't have to be so careful about saying less than or strictly less than. But for a discrete random variable, that can make a huge difference because singletons have probabilities. And so the key idea of the proof was we want to, look at, the probability that x was greater than or equal to a is the integral from a to infinity of the density. And over here, we can use the fact that x over a, what is that going to be? In this range, what can you say about x over a? If we're integrating from a to infinity. So if x is at least a, what can you tell me about x over a? It's greater than or equal to 1. And so then the idea was we want to look at the expected value of x because it says that's what the answer is. So we know that that would be the integral from 0 to infinity of x times the density. And then as long as we're doing this, let me just. Okay. And so if I want to integrate something like that, I can just now put in a divide by a. I will make things, I can't make things large if I restrict the integration to just be from a to infinity. And now in this range, I can drop the x over a and replace that with 1. And so whenever you're doing estimates, you always want to ask, how much am I losing? Well, the larger x is from a, the worse it is to replace x over a with 1. If there's probability between 0 and a, dropping that is bound. So this gives me an upper bound, and I want to get a sense of, is this a good upper bound? And we did some calculations, of what can you say in various settings. But what I hope you got from this is a very natural way to try to attack the problem. I'm telling you, I'm looking at things in terms of the expected value of x over a. So let me look at that quantity. Let me see the definition of the expected value of x. And now that I have the definition, let me work with it. Okay. I'm not going to go through the problem. This is, I think, straight from the textbook. If not, it's over here. If we have the U.S. Mean income is 60,000, what's the probability that a household chosen at random has an income of at least 120,000 or at least 1 million? We will assume that incomes are non-negative. Is this a reasonable assumption? Well, so the question is, what do you mean by income? If you have money invested in the stock market, you could actually have a negative year in terms of your household. So do you count? So it depends on your definition of income. For the most part, we really do not assume anybody is working for negative amounts of money, right? So we will assume that this is a situation where it's reasonable to assume 0 is the smallest. And so this can give us some estimations as the probabilities of events. It's not too hard to apply Markov so long as the conditions are met. And this is true like everything in life. If you want to use a result, you have to make sure the conditions are satisfied. All right. And so again, I'm rewriting Markov's inequality now. So instead of saying, what's the probability that I'm at least a, I'm asking, what's the probability I'm L times the expected value? That's at most 1 over L. And again, the whole thing is to measure things relative to the natural scale. The only quantity I have is the expected value. So because that's the only quantity I have, I should measure things relative to that. Am I twice the expected value? Am I half the expected value? Am I 5 times the expected value? So looking at L times the expected value, that's a reasonable thing to do. So you could ask, what's the probability you are in the top, so let's say you're 10 times the average income. That would be a reasonable question to ask. The probability is at most 1/10. Okay, if you had more information, rather than looking at a multiple of the mean, what would you use for your measurement? The variance, not quite. You're close. The standard deviation, right? Nobody wants to talk about how much do I weigh plus or minus so many square pounds or square kilometers, right? Or my height plus or minus so many square meters. You want to take the square root of the variance. This is why we define the symbol for the variance as sigma squared, to highlight that we want to take a square root. So if I had the variance, I would love to measure things in terms of that. But not every distribution has a finite variance. And so for something like this is a very natural thing to do. Okay, so now, not surprisingly, the very next thing, Chebyshev's inequality, assume we have a finite mean and a finite variance. What I'm going to do is I'm going to look at the probability that I take on a value that's k standard deviations away from the mean. So these are two really natural things to do. I'm looking at fluctuations about the mean. The mean is the most common value. So it makes sense to talk about fluctuations about the mean. What's the correct scale to study things? The correct scale to study things is in terms of the standard deviation. So this is a really natural thing to look at. And what it says is the probability that you're at least k standard deviations from the mean is at most 1 over k squared. So as k gets larger, not surprisingly, the probability gets smaller. Are there any values of k where this is useless? So when would this be useless? If k is 1 or less than 1. So it's useless if k is less than or equal to 1. It tells you that you have at most 100% chance of something happening. There's usually faster ways of proving you have at most 100% chance of something happening, right? Similar to Markov, that, if I choose too tight of a window about what I know happens on average, everything could be masked there. I could have a distribution where all the probability is at the mean. So I can't do better than 100% in situations like that. But as I start to get further and further away from the mean, then I start to have a non-trivial bound. And again, we can play the same game if you want to talk about the probability that you are less than k standard deviations, it would be 1 minus 1 over k squared. So in many situations, you're going to have x is going to be a limit of maybe a sum of random variables. And so you might have the standard deviation is going to 0. And so you might have things getting tighter and tighter and tighter. Eventually, what we hope to have is the central limit. Which do you think is better, Markov or Chebyshev? If I give you a distribution, which do you think is going to give you a better result? Why Chebyshev? Yeah, Chebyshev uses more information, uses more info than Markov. Uses the standard deviation.
Excuse me,
so
sorry.
the hope
If
is
you
that by using
share
more
your
information,
it's not
is there an echo now? Okay. By using more information, we hope that we can do better. Oh, am I not screen sharing?
Yeah.
Oh, if I'm not screen sharing, then that's really bad. Thank you. Then that means none of this has been recorded so far. Thank you. All right. So let me quickly go back to just the previous few pages. Okay, so we just started off with, this is lecture 17. The things we were doing today, fortunately, don't really need too much for the screen for that. We were talking about Markov's inequality and just, showing good ways to do the integration. We then passed to a example, and, fortunately, again, verbally is not too bad for that. And then again, verbally, fortunately, not too bad for this as well. Thankfully, we have not been doing long, tedious calculations, just measuring things in terms of L times. All right, but now as we started to do calculations, now it's actually good for the screen to be shared. So thank you. Okay. So the big thing to notice is at the end, this point over here, that we're measuring bounds for the probability, and it's decaying like 1 over k squared versus 1 over k. So that's a quadratic decay rather than a linear. It's not quite apples and oranges because we're now measuring things in terms of standard deviations away from the mean, and the other one was multiples of the mean. So it's not quite the same thing. Can't be the same thing because for Markov, we don't necessarily have a standard deviation. Okay. So how do we prove this? So the proof is in the book. I'll go through very quickly 2 different proofs. One of them is to show that Chebyshev follows immediately from Markov. And what you do is you just take as your random variable w to be the x minus the expected value of x squared. Clearly, this is a non-negative random variable because we're squaring something, which means we can use Markov. And so we apply Markov to w. What's the expected value of w? That's, by definition, it's the variance of x. And so when you just unwind all the definitions and whatnot, you get Chebyshev follows immediately from Markov. Okay. The other way to prove it is to do something that looks really similar to what we did for Markov's proof. Which shouldn't really be surprising, because if I'm using Markov's theorem, I'm basically just using this proof. It's just a question of how much in your face do I want to be that I'm doing this calculation. So in the first proof, I was kind of hiding the fact that I was looking at a very clever way of writing expected values, and certain things are more than one. And in this one, I'm just being a little bit more upfront about what I'm doing. If I want to calculate the probability that I'm at least k standard deviations from the mean, well, I just integrate over all x such that x minus mu in absolute value is at least k times the standard deviation. And so now, because, oops. Hello, are you trying to get into the class? Yes. Okay. And so let me just make some people co-hosts. Okay. Thank you. Yep. Okay. So because we're only looking at x such that x is at least k standard deviations from the mean, I can replace the quantity 1 with x minus the mean over k times the standard deviation squared. And that's only going to make things the same or larger. And then I just pull out the k times the standard deviation from the denominator, and I'm left with x minus mu squared. Oh, well, that's looking a lot like the variance, except I'm only integrating over some of the x. So if I expand over all the x, I can't make things smaller, and that's where the standard deviation of x squared comes out from the integral. They're going to cancel, and you get a 1 over k squared. And so, this is, Chebyshev's theorem. And what you could do is you can look at different distributions, and you can say, what's the probability I'm at least 5 above the mean? And do it for Markov, do it for Chebyshev, and see what's better. Do it for, say, an exponential random variable. Do it for a uniform random variable on 0 to 100, and see who does better. I would expect Chebyshev to do better. What is the advantage Markov has over Chebyshev? So it's more than you don't need to know the standard deviation. You're right that you don't need to know, but it's more than just that you don't need to know. There's that, but there's something else. It's related to the standard deviation. I've already said it today. It doesn't need to have a standard deviation, right? So it's more than just we don't need to compute it. We may be in a situation where it's not available. And so the hope is, in general, the more you know, the more you can deduce. So what I want to do is I want to do a subset of a talk I've given many times on some mathematical stuff. I hope everybody can solve linear and quadratic polynomials. If I give you ax plus b equals 0, this is not that hard to find. Move b over, divide by a. We'll always assume the leading coefficient is not 0. If I give you a quadratic, this is not that hard. How many of you are pure math majors? So sometimes if you're a pure math major, you have to take abstract algebra, and you might take Galois theory as well. It turns out that there are formulas for degree 3 and degree 4 polynomials that give you the roots in terms of the coefficients. Once you hit degree 5 and higher, there's no longer such a root, and you have to estimate. Here is the formula for the degree 3. Now, you could make life a little bit simpler. So what does WLOG stand for? Without loss of generality, I can assume A equals what? If I give you a cubic, without loss of generality, what can I assume about A? We're assuming A is not 0, so I can renormalize and make A equal to
1.
1. Just divide through by A. So A equals 1 if non-zero. And then that just replaces B with B prime, which is B over A. And so if you want, it's enough to just consider polynomials where A equals 1. All right, that still gives me a huge nightmare through here. The next is, without loss of generality, B equals 0. We can send x to x minus r. And if you do a little shift like that, you can change the x squared coefficient, make the x squared coefficient 0. Making A equals 1 makes the formula a little bit nicer, but not that much nicer. Taking B to be 0 makes things a lot better. And again, these are tricks you want to learn as you're studying problems. What can we do to make the expressions simpler and easier to study? A lot of you might be thinking, I'm a stat major, I don't care about abstract algebra, why is he wasting my time on this? And so for those of you who are thinking that and being polite enough not to say it out loud, when we get to the central limit theorem, what are we going to do? We're going to be subtracting the mean. We're going to be renormalizing by dividing by the standard deviation. This is a common technique. Even if you're not doing pure mathematics, we're going to do this to make the expressions easier to work with. So this idea of how can we take a nightmare and simplify it, this is something you really want to do. Now, of course, you could also do the quartic. This is just one of the 4 roots. And again, you could play the games, you could adjust so that A equals 1, you can adjust so B equals 0. But these become involved and hard to work with. Can we numerically approximate the roots? So how would you numerically find the roots? So how many of you have seen divide and conquer in some class? It's one of the greatest algorithms of all time. So imagine I have a continuous function. I know I'm negative at 0 and I'm positive at 1. What must happen? I have to cross, right? This is not Star Trek where I have a transporter and I can instantaneously move from one place to another. The reason Star Trek created the transporter is budget issues. They didn't have a budget for a shuttlecraft. So what if instead of a shuttle, what if we just push a button and they instantaneously appear on the planet's surface? Then we don't have to build that set. Yes, let's do that, right? In the real world, we don't move instantaneously from one point to another. So if I know I'm negative at one point, positive at another, I must cross in between. So what I can do is I can then check the midpoint. If the midpoint is 0, I found the root. What if the midpoint is positive? Where must the root be? First half or second half? First half. If the midpoint is negative, where must the root be? Second half. I'm actually using bad language. I'm saying where must the root be? There could actually be multiple roots. It could be something like this. I just know there has to be at least one root. And so I can use divide and conquer to find at least one root. In some advanced math classes like complex analysis, you actually learn techniques to count how many roots there are. And so what we can do is we can basically, it's called the method of divide and conquer. If you're negative at A, positive at B, look at the midpoint. If that's a root, you're done. If not, if it's positive, then the root is somewhere then A root is somewhere between A and the midpoint. If it's negative, it's somewhere between the midpoint and B. And then just shampoo mathematics. Lather, rinse, repeat, lather, rinse, repeat, lather, rinse, repeat. Keep doing this. Every time you do this, what happens to the size of the interval where a root lives? It gets smaller. By how much? 1/2, by a factor of 2. Who are my computer science majors? Okay. How many megabytes in a gigabyte? Roughly, it's not 1,000. How many are there exactly? 1,024. Is this because computer scientists are not classical scholars and don't know the suffix mega and giga? That they didn't go to a liberal arts school like Williams and learn stuff like this? Why do computer scientists have 1,024? Power of 2. 2 to the 10th is 1024. So every 10 iterations, it's approximately 1/1,000 or 3 digits. So if I want to get 3 digits accuracy, I basically do this 10 times. If I want 6 digits, I do it 20. If I want 9 digits, I do it 30. In some sense, this is good. I know how long I have to compute to get to a given level of precision, but it's not particularly fast. I don't have to compute the value of my function exactly. All I have to do is tell, is it positive or negative? So a lot of times I can actually do that calculation faster than determining the actual value. I only have to get the value close enough to know, is it positive or negative? And so here's a little table trying to calculate the square root of 3, which is about 1.7320508. And after doing 10 iterations, I know it's somewhere between 1.730469 and 1.732422. So I know it's roughly 1.73. It's not horrible, but it's not great. And that's a lot of effort to be on the order of 2 or 3 digits. What I want to do now is I want to show you Newton's method. This is what pushed me to math and physics. I was a double major, I stayed a double major, but just seeing this showed me the power of mathematics. There's 2 parts of calculus. There's the differentiation, the rate of change, and there's the integration, the area under the curve. The big idea in, one of the big ideas in calculus is you can replace a complicated function with a straight line. And for short amounts of time, the straight line is going to be a good approximation if your function's differentiable. If you want a better approximation, you start to do Taylor series, and you approximate it with a quadratic, with a cubic. The more terms you have, the better the approximation, but the harder it is to work with. So imagine I take my function and I approximate it with a straight line. So again, if anybody wants to, I'm always happy to meet and go over the details. At a high level, if I have my function and I have some point x naught, the value of the function at that point is f of x naught, the slope is f prime of x naught. I can calculate the equation of the tangent line. Y minus f of x naught is f prime of x naught, x minus x naught. And the idea of Newton's method is you take your function at a point, and then you find the tangent line approximation, and you see where that hits. And we call that point x1. And then we would calculate the tangent point of that and see where that hits. And you keep going and going and going. And that's going to give you a sequence of points. And the hope is that that sequence of points will converge to the true root. Okay? And so this would be calculating x0, x1, x2, and so on and so on and so on. If I give you the function x squared minus 3, the roots are plus or minus root 3. After you do a little bit of algebra, you get a nice formula. The next guess, xn plus 1, is 1/2 the previous plus 3 over the previous. And you want to always ask, is this formula reasonable? If you were truly lucky, what would you get for one of your values for one of your guesses? If life was good, what would your guess be at one point? What are we trying to find? We're trying to find the square root of 3. What would happen if xn equals square root of 3? What would xn plus 1 equal? It would be 1/2 root 3 plus 3 over root 3, which is equal to root 3. So if you happen to hit the root, you stay at the root. That's really good, right? If I'm trying to approximate the root, once I have the root, I don't want to keep moving. What if I guess that the initial value for the square root of 3 is 100? What do you think? Good guess or bad guess? Really, really bad guess, right? I should not be guessing 100 for the square root of 3. If I guess that, what would x1 be approximately? If my initial guess is x0 is 100, what would my next guess be approximately? 50. What would my next guess after that be approximately? 25, 12.5, 6.25 approximately. So we can see it's very quickly falling. And so if I start off with a bad guess, okay, it's going to take me a while, but then eventually I'll get to a point where it's going to be somewhat reasonable. And then it turns out this has remarkable convergence properties. So I have recorded the first couple of values. If you start off with a rational number, the next guess will be rational, so you'll stay rational. So if I start off with 2, I hope we all agree that 2 is not a particularly good guess for the square root of 3. The next guess is 7/4, or 1.75. That's not bad. The next guess is 97.56, 1.73214 versus 1.73205. Okay, The third guess, 18,817 over 10,864, 1.732050810, 1.732050875. We're off by 0.000000025 approximately. After three guesses, after three iterations. Compare this to divide and conquer. Okay, night and day. If I just do the first five guesses, you have to go this far with the first five guesses before you find a difference. And for those of you who are computer scientists, you really don't want to work with the square root of 3. You want to work with ratios of integers. This is a ratio of integers with a tremendous number of decimal places that agree. Why is Newton's method beating the shit out of divide and conquer? What's the difference between the two methods? What is Newton's method using that divide and conquer is not using? The derivative. Newton's method uses the derivative. It's using more information. Not every function is differentiable. So I can't always use Newton's method. But when I have a differentiable function, Newton's method might be far better. It turns out that for functions like this, if you want to find square roots, every iteration doubles the number of decimal digits. Remarkable. So let's play a simple game. So consider the function x squared minus 1. I'm not assuming any issues with people finding the roots of this function, but I will give it to you. It's 1 and negative 1. All right. We can apply Newton's method to try to find where would I converge. So for instance, if I start off with x equals 100, I would get 100 plus 1 over 100 over 2, okay, about 50. If I keep iterating, do you think I'm eventually going to converge to the blue root of 1, the red root of negative 1, or not converge at all if I start off at 100? Blue. Which numbers do you think converge to blue? Numbers greater than 0, we think numbers greater than 0 should converge to blue. And where do you think should converge to red? And then the battleground state, 0, right? And we should not be able to put in 0. Good. It blows up at 0. And it turns out this is correct. If you apply Newton's method to something like this, anything greater than 0 will converge to 1, anything less than 0 will converge to -1. A modification of this works for other quadratic problems. In math, we love to generalize. Let's look at x cubed minus 1 equals 0. So this has 3 complex roots. I'm sure everybody remembers from high school, polynomial long division. Looking at this, I know x equals 1 is a root, so I can do the polynomial division, get x squared plus x plus 1 is the other. I can use the quadratic formula. I can write down the 3 roots. And so if I put down the 3 roots in the complex plane, I will call them red, blue, and green. Can you give me a rule for when you think I converge to red, when I converge to blue, when I converge to green? You gave me a rule before. How would you say your rule before? What would be the nice, simple way to say that rule? You converge to the root that is closest. What rule do you think is going to go on here? Closest. And so how would we figure out which ones are closest to red, to blue, to green? Find the distance. And so it would be something like this. Clearly, anything in the upper half plane will be closer to red than it will be to green. So that gives me the purple line, that's the negative axis. And then I just connect the red and the blue and draw the line, going through that. And so this gives me 3 regions. So does everyone agree that, this should be the red region, this should be the blue region, and this should be the green region? Math does not always generalize as you expect. It's mostly true, but as you get near the border, strange things happen. If you have really good vision, you might notice that there is a YouTube link over here. And so I'll send you that link. It zooms in. When you look at this picture, is there any part of the picture that looks a little hard to see? Yeah, the center. Yeah, a lot of stuff is happening on the center, and it gets tough to draw what's going on there. So I love this problem. It really highlights, I was smart, and I also put the link down over here to make it easier to see. Sorry. Okay. So this is a great example of the more information you know, the better you can do. But you've got to be careful about taking something and pushing it in a region you have no justification for claiming that it still holds. Just because things worked well with quadratics does not mean it's going to work well with cubics. This is one of the most common mistakes people make. If you think back to the financial crisis in 08-09, oh, these are independent, we'll keep assuming that these, we have no way of being able to make those assumptions. Be very careful when you push things from one region where you have knowledge to another. So I really want you to get that as a lesson out of this. All right, so now I want to shift to the exponential function. So hopefully everybody has seen this before. And if we can differentiate term by term, again, this needs to be justified. But if it's allowed, then it's the same as the following. So take the derivative, and I can, of course, move out the n factorial. And then that's going to be the sum, and goes from, I might as well go from 1 to infinity of 1 over n factorial and x to the n minus 1. This is the same as the sum, and goes from 1 to infinity of 1 over n minus 1 factorial x to the n minus 1, which is just e to the x. Just let m equal n minus 1. So n going from 1 to infinity is the same as m going from 0 to infinity. This is just differentiating term by term. The derivative of 1 is 0, the derivative of x is 1, the derivative of x squared over 2 factorial is just x over 1 factorial, x cubed over 3 factorial, its derivative is 3x squared over 3 factorial, that's just x squared over 2 factorial. So if we can interchange the derivative with the infinite sum, then the derivative of e to the x is e to the x. That has to be justified. The reason why we can do this is the factorial function grows so rapidly that this is allowed. But I can give you examples of functions where you cannot interchange the derivative and the infinite sum. So that is not always possible. What is e to the x times e to the y? How many people say it's e to the x plus y? It is, but that's a theorem. What is e to the x times e to the y actually? We don't, e to the x plus y is equal to the sum, k goes from 0 to infinity, of x plus y to the k over k factorial. E to the x, e to the y is the sum, n goes from 0 to infinity, of x to the n over n factorial. The sum m goes from 0 to infinity, y to the m over m factorial. That's what it is. If mathematics had good notation, we should not be writing e to the x for this function if e to the x times e to the y is not e to the x plus y. This would be horrible notation. When you see this, you should be thinking, well, just combine the exponents. What's x squared mean? It means x times x. What does x cubed mean? X times x times x. X squared times x cubed, I just have 5 x's, it's x to the 5th. I understand integral exponents. I understand rational exponents. What does x to the 1/2 mean? It means I'm searching for a y such that y times y is x. I understand something like that. What does it mean to raise something to the root 2th power? What does it mean to take a number like e, which is irrational, and raise it to potentially an irrational? The formula for e to the x, that makes sense for any value of x. Even if x is irrational, notice we're just taking it to integer powers. So the definition of e to the x works for all input x. And so now you have to show that these two sums are the same. This sum, with a little bit of work, it's the same as the sum k goes from 0 to infinity, the sum L goes from 0 to infinity, x to the L, y to the k minus L, over L factorial k minus L factorial. And what I'm doing is I'm saying, well, look, when I multiply everything out, I might as well group all the x's and y's that have a common number of terms. I want to look at all the times n plus m equals k. Okay? When you look at this, you've got an L factorial and a k minus L factorial. Does that look like anything you've seen before? I'm sorry? It looks a lot like a binomial coefficient. What is it missing? Nope. Almost. Not an L factorial. A k factorial. So can we just put a k factorial in the numerator? No, but if we do k factorial over k factorial, that's legal. And then this becomes the sum, k goes from 0 to infinity, 1 over k factorial. The sum, L goes from 0, it's not infinity, sorry. The L sum only goes up to k. What I wrote is actually not wrong, because a negative number factorial is going to be infinity, so it would actually be fine by definition, but I should not be writing that. I should be writing the L sum goes up to k. And so now I would have k factorial over L factorial, k minus L factorial. That's just going to be k choose L. And then I'll have x to the L, y to the k minus L. What does this quantity equal here? What's that equal to? It's just x plus y to the k. That's the binomial theorem. So this is the binomial theorem. So you have to prove that that you're allowed to interchange the orders of sum, that you can regroup things. This is why you take multivariable calculus. Every now and then, we're supposed to use the classes you have as a prerequisite. And so in multivariable calculus, you have two techniques that you learn. One is to change variables, and the other is to change the order of integration. And that's essentially what we're doing here. We're essentially just changing variables, and we're just integrating over, but instead of doing integrals, we're doing sums. So this gives us some of the key properties of the exponential function. We're going to need to use this when we do the central limit theorem. Why? Well, what's the density of the normal? E to the negative x squared, right? We have to understand a little bit about the exponential function if we want to do the central limit theorem, because it involves the exponential function. So we need to know a little bit about its series expansion. Okay, so the next is a little bit of a review in the beginning. I have no idea why we have these modern art boxes over here. I'm not sure where they came from, but okay. So the first is the gamma function, which we've seen before, and we've talked numerous times about why we're defining it as s minus 1. The gamma function will have, gamma of n plus 1 is n factorial, n is a non-negative integer. And we've seen that the gamma function is very important. It showed up in the Weibull distribution, the gamma distribution, the beta distribution. It comes in all the time. So one of the big results is Stirling's formula, that n factorial is approximately n to the n e to the minus n square root of 2 pi n. And by that, what do we mean? It means, well, if you take the left-hand side and divide by the right-hand side, that goes to 1 as n goes to infinity. More can be done. we can have an expansion that tells you how much are you missing by what's the first order correction. A lot of times in the limit, we only care about the main term. Sometimes we care about the secondary term. Any physicists here or potential physicists? Okay. Sometimes in physics, you have terms that are going to infinity. So you subtract them and you look at what's coming left over and try to deal with the infinite that's happening. So we can not only quantify the main term, we can quantify the correction. Does n factorial grow rapidly? Yeah, huge, right? If n is 100, to go from 100 factorial to 101 factorial, you're increasing by a factor of 101. That's a huge increase. If you look at the error term is 1 over 12n. Percentage-wise, as n gets really, really large, 1 over 12n is small. But if you take 1 over 12n and you multiply it by a huge number here, that's huge. Who would like 1,000th of how much money I have in my wallet today? Yeah, I mean, you might as well. It's going to be less than a cent, right? Who would like 1,000th of Elon Musk's net worth? Or Jeff Bezos' yeah, right? Which would you rather have? 1/10 of my net worth or 1,000th of Jeff Bezos' net worth? I would much rather have a smaller percent of an immensely larger number. So whenever you're looking at things, you always have to ask, is it an absolute or is it a relative comparison? The number, the amount that I'm off by, it could be a huge number, but it might be very small relative to the main term. So relative to the main term, what I'm getting from this is small, but it could still be a very big number compared to other things in play. All right, so we want to get a sense of, oops, I think I went the wrong direction. We want to get a sense of how fast is n factorial growing. So can somebody give me a weak upper bound for n factorial, something that you know is true? N to the n. So this is n minus 1, 3 times 2 times 1. So we know clearly it's less than n to the n. Give me a lower bound. It can be a weak lower bound. 0, 1, and all of those would work as weak lower bounds. There's a huge difference in size between n and n to the n. And so the question is, can we get a sense of, what is the true size of something like this? Yeah, okay. And so one of the things I could do, and the book goes through this in a lot more detail, is we have 1 times 2 dot 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 times, let's say, n halves, n halves plus 1 dot 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 n. Everything in here is between n halves and n, and everything in here is between 1 and n halves. So I get a lower bound of 1 to the n halves times n halves to the n halves, less than equal to n factorial, less than equal to n halves to the n halves, n to the n halves. And the way I get the lower bound is I use the smallest value in each half n over 2 times. The way I get the upper bound is I use the largest value in each half n half times. And if you look at what I get now, well, they both now have an n halves to the n halves. The difference is the upper bound has an extra factor of n to the n halves. They still differ by a lot, but it's not as bad. Instead of splitting things into 2, what could I split things into? After splitting into 2, what's the next easiest thing to do? Not 3, 4. And after 4, 8. This is very similar to divide and conquer. So we call these dyadic decompositions. And so for the upper bound, for the next one, you would get n factorial would be less than equal to, n fourths to the n fourths, then 2n fourths to the n fourths, then 3n fourths to the n fourths, then n to the n fourths. And if you look at this, I'm going to have 1/4 times 2/4 times 3/4 times 1 to the n fourths. And then I'm going to have n to the n fourths, n fourths, n fourths, n fourths. That's an n to the n. Okay. So over here, this is going to be 2/4 is 1/2. So this is going to be 3/16 to the n to the n, or n to the n 16/3 to the negative n. Stirling's formula was saying I should be getting n to the n e to the minus n. E is approximately 2.7. 16/3, okay, 16/3 is more than e, but as I do this more and more times, it's going to get better and better and better. And so this is hopefully giving you some feel of the fact that your Stirling's formula is reasonable. I'm seeing the n to the n dependence. I'm seeing something looking like a constant to the minus n. It's not a proof, but it's giving you a flavor that this is the type of result to get. And again, I know I sound like a broken record. You're going to use very little of the facts you learn in college. What you're going to use is how to attack a problem, how to get some intuition, how to get a feel for what it looks like. And that's what I'm really trying to emphasize today. You can read the book, you can talk to me in the TAs if there's a specific fact that you're having trouble with. I really want to emphasize, how do we look at problems? The other thing is to see if a formula is reasonable. What kind of test can we do? Well, does everybody agree that n plus 1 factorial over n factorial should just be n plus 1? Let's check and see what would we get by Stirling. So n plus 1 factorial over n factorial, Stirling says that would be n plus 1 to the n plus 1, e to the negative n plus 1, square root of 2 pi n plus 1, and then we divide by n to the n, e to the minus n, square root of 2 pi n. So this is just checking to see, is Stirling's formula reasonable? I know n plus 1 factorial over n factorial should be n plus 1. Is this close to n plus 1? If it's not, then I don't believe Stirling's formula. Notice that the 2 pi's are going to cancel. So if Stirling's formula, if it, instead of being square root of 2 pi, if it was supposed to be the square root of 4 pi, I wouldn't be able to detect a difference like that. So already it tells you, when we're doing something like this test will not detect multiplicative rescale errors. I've got an n plus 1 to the n plus 1, that's an n plus 1. Then I have an n plus 1 over n. That's 1 plus 1 over n. Is everybody comfortable with that? N plus 1 over n to the n is just 1 plus 1 over n to the n. All right, the e to the negative n plus 1, e to the minus n, that's just an extra e to the minus 1. The square root of pi's cancel, and I'm left with the square root of n plus 1 over n. All right, so this is n plus 1, 1 plus 1 over n to the n, e to the minus 1, square root of 1 plus 1 over n. As n goes to infinity, what does 1 plus 1 over n to the n go to? Yeah, this is another definition of e. E to the x is also the limit as n goes to infinity of 1 plus x over n to the n. That's an alternate definition. This is the compound interest formula, which you might have seen. So this is going to e to the 1. And as n goes to infinity, this goes to 1. So this over here looks like 1. So again, this shows you that Stirling's formula is reasonable. It's not a proof, but it has at least good properties. And it really is looking like a nice multiple of n plus 1. I will risk showing the slide from calculus the integral test? Does this seem vaguely familiar? So if I give you a function that's non-decreasing or non-increasing, I can approximate a sum by an integral. And the amount I'm off by is related to the first and the last terms. Whenever you see a product, you should have a Pavlovian response. Take a logarithm. So early in the semester, some former students of mine made a list of Millerisms. And one of the high points was, if you see a product, take a logarithm. What's the log of n factorial? The log of 1 plus the log of 2 plus the log of 3 all the way up to the log of n. And we know we can approximate sums with integrals. So the sum of the logs is approximately the integral. And so this is just going through the steps of the integral test and showing you that the log of n factorial is approximately integrating the log of t from either 1 to n or 2 to n plus 1, something like that. Does anybody remember what function has derivative log of t? Does anybody remember the derivative of log of t? 1 over t. So everybody knows the derivative of the natural log is the 1 over function. But what function has the derivative? So unfortunately, that's a little bit more involved. One way to do this is the method of divine inspiration. I claim it's t log t minus t. Well, once I give you a proposal, you just have to take the derivative. There is no excuse for getting a derivative wrong. Okay, I'm sorry. I know this is 21st century America and we're supposed to be very supporting. I'm not that kind of professor, and I know this is being recorded. No excuse for getting a derivative wrong. I can't stump you. You just keep applying the rules of differentiation. Is it a product? Is it a composition? Is it a sum? And then I just keep hammering away. Antiderivatives, integrals, completely different. Absolutely acceptable not to know how to do it. Almost all of them cannot be done in closed form. One thing is I could try by taking, t log t. And if I take the derivative of this, I use the product rule. The derivative of t is 1, so I get 1 times the log of t minus t times 1 over t. That's log of t minus 1. Oh, wow. T log t is really close to having derivative of log of t. I'm off by 1. So let me correct that. And that's where this minus t comes from. It comes from correcting that. So a lot of times in life, you don't have to know the solution immediately. You just need to get close and then correct. And so I start off with t log t as a reasonable thing. As a nice exercise, do you think you can find a function whose derivative is log squared of t, whose function has derivative log cubed of t? So I'll make that extra credit. Find a function, you can't use the web, can't talk to anyone else. Find a function whose derivative is log squared, log cubed, and in general, could you find log to the n? Do you have something that you could try, and then if it doesn't work, correct? This is a great philosophy in life. So many people just freeze up because they can't immediately see how to solve the problem. Don't solve the problem. Get part of the way there, and then reassess where you are and correct from that point onward. And so if you apply this as the antiderivative and use the integral test, you then get, at the end of the day, that n factorial is a little bit more than n to the n e to the minus n times e. I don't know if I've done everything correctly. But we were supposed to have square root of 2 pi, and we have e over here. You can get better than this if you do a little bit more work. You can get the square root of n coming into play by taking the average of the extreme points. I do want to do that, but I know I'm probably the only one who wants to do that. I'll just use a little bit more advanced things like the Euler-Maclaurin formula to do a better version of the integral test. So you can improve things a little bit. Okay. How many of you have seen the Poisson distribution? So the Poisson distribution is often used for accounting what's the probability of a certain number of failures happening in a certain amount of time. What can you tell me about the number of failures? What kind of quantity is it? It's an integer. This is either it failed or it didn't. How many traffic accidents do I have in this intersection? And so the possible values are 0, 1, 2, 3, 4. This is another one of our nice discrete random variables. So the probability that we have n is going to be lambda to the n e to the minus lambda over n factorial if n is a non-negative integer and 0 otherwise. And so lambda is the parameter, and it's going to be greater than 0. What's the first thing you should do if I claim that this is a probability distribution? No, that's not the first thing. I'm claiming it's a probability distribution. What's the first thing you should do? Check. So is it non-negative? Yes. Does it sum to 1? Well, the sum, n goes from 0 to infinity, of lambda to the n, e to the minus lambda over n factorial. I can pull out e to the minus lambda, and I'll have a sum, n goes from 0 to infinity, lambda to the n over n factorial. But what's the sum of lambda to the n over n factorial? E to the lambda. So I get e to the negative lambda, e to the lambda equals 1. And in fact, that's why we have e to the minus lambda in the definition of the Poisson, so that it sums to 1. Lambda to the n, if lambda is greater than 1, that could be growing, but the n factorial is decaying much, much faster. So note, lambda to the n over n factorial, actually I don't need absolute values because lambda is positive, is less than or equal to lambda to the n to the n, e to the minus n. I'm going to drop the square root of 2 pi n to make things larger. This is equal to e lambda over n to the n, which goes to 0 fast. Because no matter what lambda is, eventually n is so large that n is going to be greater than e lambda. So this is dominated by a geometric series. So dominated by geometric series. So everything is going to be fine. So this is just a quick way of proving that the exponential function is going to converge by any input. How would we calculate the mean? How would we calculate the variance? So any thoughts as to how we would calculate the mean and the variance? You could do differentiating identities, right? Miller loves differentiating identities. Let's do that. How else could you do it? Go back to the definition. And then over here, I think I did it both ways. So, straightforward calculation. I'm going to apply the operator lambda d by d lambda, because that way when I take the derivative, I decrease lambda by 1, and then I bring it back up by 1. Okay. Is there any concern you have with this? So if you look at the differentiating, I apply lambda d by d lambda. I decrease the exponent of lambda by 1, and then I increase it back up. So there is an issue. It is not justifying the swapping. So the point of this is to show how easy it is to try to slip things by you. When n equals 0, the first term has no lambda dependence. It's just a constant. What's the derivative of a constant? When I multiply by lambda, what do I get? 0. This doesn't work. It's not a sum from 0 to infinity. I've got to be careful. This sum has to start at n equals 1. And so this should be from n equals 1. Can I then extend the sum down to 0? I'm sorry? Well, when n equals 0, what is 0 times? It's still 0, right? So if I extend it down to 0, it's fine because I'm just adding 0. So can extend, let's turbo extend. Can extend down to 0 as the 0 term is 0. So everything can be justified, everything can be fixed. But this is one of the problems. You can actually end up at a right point with an invalid argument. So I had to be a little bit careful. I can't just naively go through. If you look on the other side, I'm a little bit more careful and I'm moving the sum to be from 1. And so I'm just calculating n times the probability, and I'm just playing some algebra games. And so, I'll let you go through and look at the algebra. If you have trouble doing this, please see me, please see the TAs. You should be able to do calculations at this level. And now you want to calculate the variance, you would have to either take the derivative again, or you would have to calculate the sum of n squared. Or instead of doing the sum of n squared, you might do n times n minus 1 versus n squared if you want to do the variance. And then you would have to play games, and then you would have the second moment n squared minus the first moment n. Sometimes that's easier. We saw this with the negative binomial. Sometimes one quantity is easier to compute than the other, and once you have that, then you just adjust and get to the other one. So again, I strongly encourage you to make sure you can calculate the variance in both ways. So this is the Poisson distribution. Now here's a beautiful theorem. Sums of Poisson random variables. The sum of n independent Poisson random variables with parameters lambda 1 through lambda n is a Poisson random variable with parameter lambda 1 plus dot 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 plus lambda n. What does this remind you of? Where have we seen something like this before? Chi-squared, where else? Normal, right? This is another example where it's still going to be in the same family. Do I have to prove this for a sum of n Poissons, or is it enough to do for just 2? Just 2 in grouping. So if I do, x lambda 1 plus x lambda 2 plus x lambda 3 and so on. If we know it's 2 for 2, this is now just x lambda 1 plus lambda 2 plus x lambda 3, and that would be x lambda 1 plus lambda 2 plus lambda 3. Anything you see multiple times is a technique. This is a technique. We just have to prove it for the sum of 2 of them, as long as we use a general parameter. All right, so let's do that. So let's let proof. Let's let y equal x lambda 1 plus x lambda 2. So we need to figure out what is the probability that y equals n. So there's a lot of ways to do this. This is really a convolution, but because everything is discrete, I'm going to just write it a little bit carefully. This is the sum. Let's say k goes from 0 to n. The probability x lambda 1 equals k. And then the probability, what would x lambda 2 have to equal? Oh, sorry, this is k. So if I want the sum to be n, and the first one is equal to k, what does the second have to be? N minus k. Well, this is the same as the sum, k goes from 0 to n. What's the probability that the first one equals k? It's just lambda 1 to the k, e to the minus lambda 1 over k factorial. What's the second? It's lambda 2 to the n minus k e to the negative lambda 2 over n minus k factorial. Do you recognize anything here? Does anything look like something you might want to know? So we have a k factorial and an n minus k factorial. If you're really quiet, you can hear what the numerator is begging for, right? What is the numerator screaming? What does the numerator want? It wants an n factorial. So multiply by n factorial of n factorial, and that's going to give you an n choose k. And so now let's pull out all the crap that doesn't depend on n. We have an e to the negative lambda 1 plus lambda 2. We have an n factorial down below. We have a sum, k goes from 0 to n, of lambda 1. Let me write better. We have our n choose k from the binomial theorem. And then we have lambda 1 to the k, lambda 2 to the n minus k. What does this quantity here equal? So by the binomial theorem, what does this equal? Lambda 1 plus lambda 2 to the n. And so this is just going to be lambda 1 plus lambda 2 to the n, e to the negative lambda 1 plus lambda 2 over n factorial. That's exactly what it should be if it's a Poisson random variable. So we've shown that the sum of two Poissons is a Poisson. Great. Lather, rinse, repeat. We now have the sum of n Poissons is a Poisson. Okay. So we've seen the normal distribution numerous times. Its density is 1 over square root of 2 pi sigma squared e to the negative quantity x minus mu squared over 2 sigma squared. We often write n mu sigma squared to denote that it's a normal distribution with mean mu and variance sigma squared. The central limit theorem, which is one of the big things we're going to be going for, the cursor was sadly copied when I was cutting and pasting, so I will just eliminate that. All right. That if we have a bunch of independent, identically distributed random variables, and whatever the moment generating function is, we'll learn about that later. If some technical conditions happen, then we can look at the sample average, the sample mean, just basically add up all the variables and divide by n. And then if we take that and we subtract mu, which is what the average should be, and we divide by the variance of the sample mean. And what's the variance of the sample mean? Well, the variance of xn bar, it's the sum of the variance of each xk over n. And when I do the variance, if I multiply the variance by a constant, the variance changes by the square of that constant. So this is going to be 1 over n squared times the sum of the variances of the xk's. But all of those are the same. So it's going to be 1 over n squared times n times sigma squared. So it's going to be sigma over n. And that's why we're dividing by the standard deviation, sigma over square roots of n. And the central limit theorem says that this becomes normally distributed. And so I'll just end by briefly noting, and I'll let you do the calculation. Maybe we'll do this next time. I know what a Poisson distribution is with parameter lambda. The probability I take on the value n is just lambda to the n e to the minus lambda over n factorial. If I take n independent identically distributed Poisson random variables with parameter 1, then their sum is a Poisson random variable with parameter n. By the central limit theorem, that converges to being normally distributed. So if I calculate what's the probability that x takes on the value n, if I take lambda equals n, I get n to the n e to the minus n over n factorial. And that's now going to be related to the normal distribution, which involves the square root of 2 pi. So we will do that on Tuesday to show how you can get Stirling's formula from the central limit theorem. Math is related, math is connected. When you see a square root of 2 pi in Stirling's formula, you should immediately be thinking, where the hell is that square root of 2 pi coming from? One way of interpreting where it's coming from the central limit theorem. They're all related, they're all connected. All right, so this is a good place to stop. This is enough so that you can think about this over the weekend and try to see the connections. A lot of stuff going on. As always, if you ever want to chat, just email me, email the TAs. All right.